working with John, although I was probably first formally associated to you, Luke, as a at least you provided probably the money. I think, and I remember that. So
John provided the brain.
No. So we started. So previously I was in Dublin, and then I was working on W algebras, excellent conformal algebras, and at that time there arose some new constructions, the generalized integral of hierarchies, which had to do with W algebra. And I somehow brought this problem here to construct generalizations of the integral circle of hierarchies. And I remember that we started to discuss with with Luke also with discussions, and another visitor, Ian Marshall, participated. But after a while, you were probably at that time busy. So after a while, you dropped out of the thing, and yeah, so you did some other things, and so at the end we wrote. I think it's a reasonable paper in communication mathematical physics on certain classes of generalized KDB hierarchies associated with certain Heisenberg subalgebras of affine Lie algebras, and. I remember that, John, you were extremely enthusiastic at that time, for example, about the Adler constant sign construction and R matrices. So basically, I learned about that here, and these concepts will appear also on this talk. I also remember that you were also very busy, probably because of the teaching duty. So we were many times waiting for you to come for the discussion. But when you arrived, then it was very, very intense. So yeah, at the end, it was really a great experience for me, and I love to come back to you. So let me start this talk basically. So I basically spent three years on Bi-Hamiltonian structures of Sutherland type models. You know, I more or less so I report some kind of summary of what I was trying to do. So of course we all know about Calogero model, Sutherland, and similar models, and the example of these Hamiltonian particles moving on the circle. And due to some classical works of Olszewski, Perelomov, and Karlsson, Constant Sternberg in the late 70s, this was realized to be a shadow in the plateau stands of geodesic motion on the UN group by fixing the large number of constants of motion to a very specific value, fixing the moment map to a very specific value. And this is very, very influential work. And so then later people realized that, well, you can fix the causal quantities for this free particle moving on UN in whatever way, and you always get some integrable system. If you fix so here the group acts by conjugation, and you fix the moment map or the neutral charge generating that action to specific value, then you get this Sutherland model of just particles moving on the circle. But if you fix the moment map value to some arbitrary value, then you get then your reduced phase is no longer a cotangent bundle, but contains some kind of internal degrees of freedom, which people tend to call spin in this context. And here, this spin variable is just some Hermitian matrix with zero diagonal part, and it somehow controls the interaction of the particles, and it's also a dynamical degree of freedom. So this is what I call his spin Sutherland model. Then there are various generalizations, many generalizations of this model, and among the most straightforward generalizations, one may mention the holomorphic version. And you just see that all variables are not real, but complex valued, and the holomorphic system with mathematicians especially these holomorphic stuff. Some of my background is in physics, so I like if the particles move on the circle, on the line, and so on. So it is also known that the holomorphic version of the spin Sutherland model it comes by reduction from the cotangent boundary of GL&C, this complex Lie group. And then the trigonometric and hyperbolic real forms. The trigonometric one I already mentioned, it comes from cotangent boundary of UN group, kind of symmetric space with negative curvature. And then the hyperbolic one comes from the cotangent boundary of symmetric space with positive curvature, which is just the space of positive that is Hermitian, which I call PN. And it's important that this symmetric space is itself a quotient space of the GL&C over UN. GL&C you view as a real Lie group. So I'm thinking there are holomorphic spin Sutherland and then real forms that all of them are understood to come by Hamilton reduction method. So what I realized by some kind of accident, thinking about some papers, is that these cotangent boundaries which are listed there, all of them are Bi-Hamiltonian manifolds in some natural manner. I mean, of course, one of the Hamiltonian structure or the symplectic structure is just the canonical one for the cotangent boundary, but there's another one on these phase spaces in such a way that the natural Poisson commuting Hamiltonians, which I will show, they generate Bi-Hamiltonian flows, and then I sort of utilize this idea to apply the reduction technique not only to the canonical Poisson structure, but to the Bi-Hamiltonian structure. And in this way, I obtain some Bi-Hamiltonian structure for the reduced systems, for these Sutherland type systems. And then the same idea can be applied to this cotangent boundary of the GL and R group, and then by same kind of procedure, I can also get Bi-Hamiltonian structure on this associative algebra GL and R, and by a real matrix, which has to do with the Bi-Hamiltonian structure of the open Toda lattice, which we heard about. Okay, so now I have to use this. So that we all know what is a Bi-Hamiltonian system, that we have two Poisson brackets and in such a way that the Hamilton equation can be represented with different Hamiltonians and different Poisson. The same Hamilton equation can be represented in two ways, and these two Poisson structures are compatible in the sense that arbitrary linear combination satisfies the Jacobi identity. And then one important feature, which of course we also know, that if there is a sequence of Hamiltonians which satisfies this sort of recursive relation, or anyway this relation, and then these Hamiltonians are automatically in evolution, and in several integrable systems this structure appears. Okay, so one of my aims is to derive certain compatible Poisson structures. And here I am going to make use of a very basic lemma, which actually also used in our work with John here, how you obtain, for the KDV, it's also known that the first structure is a Lie derivative of the second structure, or by a sort of shift argument, the first structure comes from the second structure. So the general formulation of this mechanism is that is written here, the well-known lemma, that if we have a Poisson algebra with a derivation, and we define a new bracket by this formula, we apply derivation to the function. Then this new bracket will be, which is, you can see this Lie derivative in the language of vector. If this is in the language of the Poisson tensor, and this derivation comes from vector field, this is Lie derivative of the Poisson tensor along the vector field. And this derivative bracket is automatically, of course, anti-symmetric and satisfies the Reines identity, but the Jacobi identity doesn't hold in general. But when it holds, then this new bracket is automatically compatible with the original one. And in several examples of Bi-Hamiltonian systems, this is the mechanism whereby one obtains compatible Poisson brackets. So there's one bracket, and then some Lie derivative of that bracket gives another bracket. So I will apply this mechanism also here. Okay, so this is the plan of the talk. So first I will tell you about this Bi-Hamiltonian structure on the holomorphic cotangent bond of GL and C, and then this reduction, which gives the holomorphic spin Sutherland system. And then I repeat this for the real case, but with a different reduction, which gives the actually this kind of generalized Toda-like equation on the GL and Lie algebra with Professor Deift and Tomei and Lee considered in 89, if I am correct. And then there is another application of the same idea, basically, cotangent bond of GL and C as a real loop, and then it's another kind of spin Sutherland system. Okay, so here I just described the holomorphic cotangent of GL and C. So we have the trace pairing on the Lie algebra GL and C, and then we trivialize the cotangent bundle by right translations, and then it becomes Cartesian, a manifold Cartesian product of group with the Lie algebra. The Lie algebra is identical with the dual space through the trace pairing. And then we consider holomorphic functions on this phase, which I call M this phase space, to be short, holomorphic functions on this phase space. And then we need to do some notation. So the first variable is group value, the second variable is Lie algebra value. So for we have, I mean, this nabla one prime is, nabla one means derivative because of the first variable. So it is derivative on the group. It's Lie algebra value derivative. Basically, it's exterior derivative translated to the unit element to be Lie algebra value. And in the second variable is Lie algebra value. So we have usual gradient with respect to second variable is D2, and then it's also convenient to introduce this nabla derivative with respect to the second variable. Okay, so these are notation derivatives of functions which will appear in the Poisson bracket. And then I will also use the standard kind of Drinfeld-Jimbo type R matrix. So this GL and C is decomposed into upper triangular diagonal and strictly lower triangular part, and then difference of two projections is this basic solution of the modified classical Young-Baxter equation. So with these notations in hand, here is a formula for two Poisson structures on my phase space. So the first structure, you can recognize this Lie, the Lie bracket here. So this is basically the Lie Poisson bracket with respect to the second variable, the Lie algebra variable. So this first bracket is nothing but the canonical Poisson bracket on the cotangent bundle, which is of the group. And the second bracket contains the R matrix. In the first line, you can recognize this clearing bracket on the group GL and C with this R matrix. And then there is some which contains only the second derivatives. There is some interaction between the first and second derivative. So one feature of this bracket is that the first bracket is linear if you consider the matrix element functions on the phase space. Then on those functions, this bracket is linear, and the second one is quadratic. I will say something about the origin of the second bracket a little bit later. Now you can in principle verify directly that the second bracket also satisfies the Jacobi identity. Okay. So the one result is that actually the first bracket, that is the canonical Poisson bracket, is the Lie derivative of the second bracket with respect to the vector field whose flow is that. So in other words, you just shift the Lie algebra element of GL and C by multiple of the unit matrix and then take the derivative of the quadratic bracket with respect to that, like in KDV, really reminiscent of KDV, and then you get the first bracket. So these two brackets are compatible because of the basic lemma. And now on this phase space, there's a natural family of functions, namely this L is basically viewed as a kind of Lux matrix, and just the trace of various powers. So they are not independent because L is just n by n matrix. And then the fact is that if you consider such a function, I mean, of course, to a function you associate the vectors with the Poisson bracket, or two vectors with the two Poisson bracket. And then the sort of very easy proposition is that these natural functions, they satisfy this Bi-Hamiltonian recursion kind of relation. So they generate Bi-Hamiltonian flows on this holomorphic cotangent bundle. And here is the solution of these Bi-Hamiltonian flows. Of course, the Lie algebra variable is constant along all those flows. So these are so this means that these functions Poisson commute with respect to both Poisson structures. Otherwise the Hamiltonian vector field is given by this formula, or in short, it means that if you take the age m and age m plus 1, then the corresponding flow is just this. That L is constant, and it is the fluid orbit of one parameter group of the GLN state. So the basic point is that this is then by Hamiltonian flow, and I was surprised that this should have been known a long time, and maybe it was known, but I asked several people, they did not tell me that this was known. So this is the very basic observation. This is what I say, that some natural Bi-Hamiltonian system on this cotangent bundle. And since the cotangent bundle is an important source of other integrable systems, so this has some consequences for the reduced systems which are obtained from those cotangent bundles. So here I just remark that the second structure is obtained by some procedure from this, which I also I think learned from John, the Heisenberg double of GLNC. It is obtained by some restriction and some analytic continuation. So basically the second structure comes from Poisson Lie group theory, from the Poisson Lie analog of the cotangent bundle. And okay, and now I come to the reduction. So the very essence of Hamilton reduction or Poisson, the very essence is that we have some group action, and we just keep the invariance. We are interested in invariance with respect to the group action. We basically quotient the phase space by the group action, and then look for symplectic leaves in that quotient space. But for that to work, it's necessary that the invariant functions with respect to our group action should form a Poisson subalgebra with respect to the Poisson bracket, because then we identify the invariant functions with smooth functions on the space of orbits, and then we obtain a Poisson algebra on the space of orbits in this manner. Of course, the space of orbits is usually not a very decent manifold, but its structure is understood. So here the group action is just this conjugation. The symmetric group is GLNC itself. Okay, and I introduced this whole G is just the invariant functions. And so it's also follows from general Poisson theory through the Heisenberg double, but one can verify directly that the second Poisson structure has the property that the invariant functions close, because for invariant functions one can rewrite the second Poisson bracket in such a way that the R matrix actually drop out from it. And then these gradients of the invariant functions are equivariant, and the trace pairing is invariant. So for that reason, for the invariant functions, this structure closes. Of course, for the first bracket, it's obvious that the invariant functions close. Okay. So now I describe the always.
Is it true that for both structures that the symplectic structure that you're using is G invariant?
Yes, but the second one is not symplectic. Of course, it actually the neighborhood of the identity it is symplectic, but it is not symplectic globally. So it is Poisson. It is not for the second one. Poisson is not invariant because it is Poisson Lie theory, but the invariant functions do close. So now to describe somehow try to characterize this reduction. So by the passage just mean that let's focus on invariant functions. Focus on invariant functions. So there's some notation that, well, I denote by G0 the diagonal subgroup of GLNC, diagonal elements, diagonal matrices. And the regular part is when those eigenvalues are different. And then there is some dense open part of GLNC which contains basically the regular semi-simple conjugacy classes, if you like, or just the matrices which are conjugate to such diagonal matrix. And so I introduce this regular part of the phase space, and the zero means that this first element is diagonal matrix. And then so basically this whole M red, it just means the invariant functions on my phase space. But if I take an invariant function on my phase space, I restrict it to this submanifold. And this submanifold intersects every orbit in the regular part. And the other function can be also, the regular part is dense and open, so function can be, even continuous function can be recovered from restriction to this regular part. And so the point is that an invariant function can be recovered from its restriction to this submanifold of my phase space. So I'm going to represent the Poisson bracket of the invariant functions by some bracket of the restricted functions on this phase space. It's some kind of gauge fixing in physics language. It's a partial gauge fixing because there is still conjugation freedom with respect to the normalizer of this maximal torus, which contains the maximal torus itself and some permutations. So this normalizer is n. So I'm going to talk about some maximal torus invariant functions on this regular part and normalizer invariant and the restrictions of all the invariant functions. Okay. So then I define what I call reduced Poisson structure is the following, that I take some function on some invariant function on the regular part of the phase space, and I restrict it to this gauge, this partial gauge fixing in physics language when the group element is diagonal. And then I define the Poisson or the bracket of such functions such a way that take arbitrary invariant extension and then compute the Poisson bracket and restrict it. It's kind of usual procedure. So anyway, this is how reduced Poisson bracket is defined. So it's represent the original Poisson bracket of the invariant functions, which is invariant function, and then restricted to this partial gauge fixing. And this applies to both Poisson brackets. So in this way, these two reduced Poisson brackets will be automatically compatible because their origins are compatible. And then, well, if I have a reduced function, then I still can talk about its derivative with respect to the first variable, which is diagonal matrix. The derivative is the first variable, and derivative is the second variable. So the derivative with respect to the first variable is now I mean, it is a diagonal matrix in GLNC. And then one result is that I derive formulas for the reduced Poisson, for this reduced Poisson structure. So it is kind of in a way it goes back to work of Samuel of Transchanski. The first So both of these reduced Poisson structures contains dynamical R matrix. This is the kind of Poisson structure which was introduced by several people, basically by Lu and Chao Li and Ping Su, but not by this reduction technique, just by direct method. So it is, and what is the dynamical R matrix here? It depends on Q. So it is just that this group element is some exponential of little q, and then this is a linear operator on GL and C, and X is an element of GL and C. So the diagonal part of the result is 0. So it is 0 on the diagonal subspace of GL and C. And on the off-diagonal part, it is just given by X-ray formula. It's cotangent Heisenberg appears here. This is well-known. This is some kind of standard, very basic solution of the very basic trigonometric solution of the classical dynamical Young-Baxter equation, modified classical dynamical Young-Baxter equation. Okay, so this and the same R matrix appears in the reduced second Poisson bracket. So this is kind of similar to if this was a constant, this was a squaring bracket, but it is not constant. Okay, so this is the formula of the reduced Poisson structure, and actually these formulas also give Poisson structures on functions which are only invariant to the maximal torus, conjugation by the maximal torus, and conjugation action by the normalizer of the maximal torus. Okay, well, maybe I don't explain how these were derived. It's some kind of easy derivation. So the point is that an invariant function is uniquely determined by its restriction to this gauge fixing. And then of course also the derivative of the invariant function is recovered from the derivatives of the restricted function. And how the derivative of the invariant function is recovered from the derivative of the restricted function, this you can derive, and this contains this R matrix. And then you just plug the derivatives of the original functions into the formula, and then you obtain bracket in terms of the restricted function, and then it turns out to be what I wrote. Okay, and after that, what about some kind of reduced dynamics? So of course we have Poisson algebra on certain invariant functions in that partial, in this manifold which represents partial gauge fixing. So we can take the derivative of the derivative of an invariant function can be defined by taking Poisson bracket with respect to this trace of Lm, the basic Hamiltonians, and in this way we obtain some the evolutionary derivatives of invariant functions, and these can be represented by vector fields. But those vector fields are of course not unique because our functions are invariant. So there's some residual gauge freedom which doesn't fix completely these reduced dynamics is written here. What is reduced dynamics? So it contains this kind of Lux equation, the dynamical R matrix again, and how the Q, the diagonal GLNC matrix develops it is from the zero means the diagonal part of a matrix, so from the Lux matrix, and one can add here some arbitrary diagonal matrix which represents residual gauge transformation. But it will not change the development of the invariant functions. Okay, so we obtain this reduced system, and then actually it is known how this is. How this is related to the spin-Sutherland model which I started with. So suppose that this L is some general element of GL and C. So you can represent it by its diagonal part P and some off-diagonal matrix in this manner. It's a unique representation of an arbitrary n by n complex matrix. And actually this is a form, this kind of standard form of the Lux matrix of the spin-Sutherland model, which is known from other sources. So if you substitute this formula into the reduced first Poisson bracket, then it turns out that this P and the logarithm of capital Q, they are canonical conjugate pairs, and phi decouples them, and they satisfy some reduced Lie Poisson bracket. So from the reduced first Poisson bracket, you obtain the usual structure of the spin-Sutherland model, and but in terms of the variables, which is just L and Q, there is a second Poisson structure which I wrote. I actually did not, the form of the second Poisson structure in this parameterization seems to be complicated and it's not enlightening, let me put it this way, or I did not see anything enlightening about it. So this is then the first part of my talk, and out of this holomorphic spin-Sutherland model, with the Bi-Hamiltonian structure, one can recover the trigonometric and hyperbolic real forms by saying that the matrix L is Hermitian matrix, and the matrix Q is either positive definite Hermitian matrix or unitary positive definite diagonal matrix or diagonal matrix with positive elements, or it's a diagonal unitary matrix. Then you obtain the trigonometric and hyperbolic spin-Sutherland models, and you can recover Bi-Hamiltonian structure for those out of this holomorphic structure. Those Bi-Hamiltonian structures for these real forms also have independent derivation, as I mentioned, from the cotangent bundle of T star UN, and also from the cotangent bundle of this real Lie group GLNC regarded as a real Lie group. And these results were published in four papers. Okay, and now I come to, I'm a little bit behind, not much. I will start a little bit late, remember? So the Toda part. So this is another application of the same idea. So let's just consider GL and R. And this will be our phase space for this generalized Toda. I don't know how to call it. So let's take the R matrix, which is difference with this other constant signs R matrix, which is difference of two projections. This A is the orthogonal algebra, skew symmetric matrices, and B is upper triangular, this kind of Borel type subalgebra, upper triangular subalgebra with arbitrary diagonal elements. And then we have this R matrix. And then the property of this R matrix is that its antisymmetric part, which is actually the standard R matrix. This R matrix and its antisymmetric part satisfies the modified classical Young-Baxter, which is the same right-hand side. And in such a situation, Lie and Parmentier and Ovel and Ragnisko discovered some long time ago that in addition to the linear R matrix Poisson Beckett, or Adler constant signs or Semyonov-Tianshansky, in addition you can write a quadratic Beckett, which contains the symmetric part of this R matrix and the antisymmetric part. So this is actually always valid if you have two R matrices, which is the antisymmetric part and the original R matrix satisfy the same equation as you are on an associative algebra. But and now this is satisfied in this example of GL and R. And then we of course on the GL and R there are these I don't know, generalized Toda equations which Professor Dives considered, for example, in this matrix factorizations and integrable systems. I think that was the title of your paper in 1989. It is known, actually it was shown by Urval and Ragnisko that the symmetric matrices as well as the tri-diagonal symmetric matrices, they are Poisson submanifolds with respect to both of these Beckett. So in this way, you obtain Bi-Hamiltonian structure for the so-called full symmetric totalities, and also for the standard open totalities. Those Bi-Hamiltonian structures were known. I mean, they were known from other sources, but this is a kind of Lie theoretic construction. And what is my contribution, or our contribution with my student, is that this also comes from Poisson reduction. For the first Poisson method, the linear R method, but it comes from reduction. This is Semyonov-Tianshansky, all these are. But for the second one, this apparently appears to be new. So I take the same kind of phase space as before, but now G is GL and R, not GL and C, GL and R. And And every formula is the same, it's just a trace variable. Now it is real. And then I do take quotient, but with respect to what group? The symmetry group is this A times B. A is orthogonal and B is upper triangular with positive diagonal entries. And because of the and this group acts in this way on the phase space. On the phase space, and because of the QU factorization or Gramsci procedure, by this group action, you can remove this group element. Every orbit of the symmetry contains such an element that the group element is the identity from the GRL group. So every invariant function in the original phase space, which is say f and h are two invariant functions in the original phase space, they are uniquely represented by functions on the Lie algebra. On the Lie algebra, because the group element is brought to the unit matrix. So this is unique representation of every orbit of the symmetry group in our phase space. And then define reduced Poisson bracket, just restricting the Poisson bracket of the invariant functions to this cross section of the orbits of the phase space, and then you recover those compatible Poisson brackets written on the previous slide. Actually, you can also do this for the how do you call it, LU factorization and the Cholesky factorization, the same procedure works with suitable modification of the symmetry group, and you obtain also Bi-Hamiltonian structure for those generalized Toda flows. Okay, and now the final part of my talk is yet another application of very similar thing. So I will be a little bit sketchy here. So there appeared in the literature some generalization of spin-Sutherland model, which people call spin-Sutherland model with two spins. So there is QP variable. So this is some kind of hyperbolic model, but you see hyperbolic model that there is psi left and psi right. Psi left and psi right just anti-Hermitian matrices such that the diagonal part of their sum vanishes, and it matters. Also, there is the psi left and psi right. They matter up to conjugation by maximal torus. Okay, and now I can equip this system with a Bi-Hamiltonian structure again in the following manner. So now I start with group GLNC, but regarding the real Lie group, and consider the same kind of structure as before. And now the correct pairing on the Lie algebra is the real part of the trace, which is basically has to do with the killing form of this real Lie algebra. I will not present the killing because it's GLN, not SLN. But if it was SLN, then this would be the killing form of the real Lie algebra, or a multiple of that. So anyhow, one can just write formula for two Poisson structures on this cotangent, but the same formula before, totally same, just the pairing of is the real part of the trace, same kind of derivative. And this is Bi-Hamiltonian structure on this cotangent bundle of GLNC regarding the real Lie group. And then there are natural family of kind of free Hamiltonians. I call them free Hamiltonians, whose shadows give the commuting Hamiltonians of integrable system. So just real part of trace of J and imaginary part. And those functions, they Poisson commute with the both Poisson structures, and you can also write their flows, and the real part of the trace, those functions, they satisfy this Bi-Hamiltonian relation. And the imaginary part, they also satisfy that sort of Bi-Hamiltonian relation. And now we reduce by the action of UN times UN, by which is this copies act by left and right multiplication. And again, the invariant functions close, and now you can to represent the invariant functions in terms of reduced variables. You make use of the singular value decomposition that is every GLNC matrix can be written in this way, and this Q is such a real matrix with eigenvalues distributed like that. And then by the symmetry group, you can remove these factors. You can bring this group element to diagonal form, and also restrict to the let's go regular part when these eigenvalues are actually different. There's no coincidence. And then, okay, so this will be our kind of gauge slice of partial gauge fixing. So we represent the invariant functions by the restriction to this group element is such a positive diagonal matrix. And then again, I performed the task of deriving reduced Poisson-Beckett formula. I did not write it because those formulas are a little bit longer. But then if we now substitute this element J, we parameterize this element J. This is arbitrary GLNC matrix, but regarding the real arbitrary GLNC matrix, you can parameterize like this, that some diagonal real part of the diagonal part. This is P, and then you put here these functions of Q, and this psi left and psi right are, as I mentioned, anti-Hermitian matrices with such way that the sum of their diagonal part is 0. So this is another unique parameterization of a GLNC matrix. And if we substitute this parameterization to the reduced first Poisson-Beckett, then and also we reduce first Poisson-Beckett, and also this Hamiltonian, which is the one-half trace of J squared, then you obtain this formula, this Sutherland model with two interacting spins. And I was somehow happy that this work appeared this year in nonlinearity. And actually, these kind of models were introduced before by my colleague Gabor Pusztai, who was also here a postdoc with John. He's from the same city as me, and more recently by Kravchev, Levin, Olszewski, Zotov, and also Reshetikov, they developed similar models, but they did not touch upon Bi-Hamiltonian aspects. So in conclusion, so the whole content of my talk is that I realized that these phase spaces are in some natural manner Bi-Hamiltonian manifolds. And since the reduction of, and also equipped with some natural Bi-Hamiltonian flows, so two Poisson structures and these trace functions, these natural convoluting Hamiltonians. And by some standard reduction procedures of these manifolds, when applied to their Bi-Hamiltonian structures, then they give Bi-Hamiltonian structure for certain reduced systems, which were already considered before, even in this reduction context, but only considering the canonical Poisson structure upstairs, not this Bi-Hamiltonian structure. And by the way, all these reduced systems are more or less proved to possess the property of degenerate integrability on generic symplectic leaves in the reduced phase space. So they are not only legal integrable, but it's kind of.
Any questions or Mercy?
Thank you for the talk. When we began thinking together with Carl Collins-Tillet and Lou Charlie about the Toda limits on non-symmetric real matrices, then we wanted to see this matrix structure as coming from as a new Poisson structure. So then what we found we had to do was to introduce new multiplication law on matrices.
Yes.
Do you see that structure? Yeah.
I think that this new multiplication wasn't it just the dual, I mean the R matrix structure, that you represent you represent a matrix as a see how to put it, GLNC matrix or GLNR matrix, or let's call the GLNR matrix. You represent it as an orthogonal group element and the Borel element. And with respect to the linear R matrix structure, these are independent. They satisfy their own product rule. I mean, as if they commute under the R matrix structure. And I think if you represent this, you write some GLMR is as a manifold. It is UN times Bn is Borel, and so there's a diffeomorphism between those. And if you put here the multiplication rule of the product group, and moreover you have to make one of them the inverse or the opposite multiplication, opposite order, and you pull it back here, then I think that is the modified multiplication.
And that's the structure because does it show up here?
I think yes. I think this is. Yeah, I looked at your paper. Yes, so I think it is really related. But you also use some infinite dimensional algebra there. If I look,
it's just that the integrals, some are rational, and some you need a Riemann surface form to.
Yeah, you were looking for the action, this generalized action angle, not angle in inverted commas variables. I did not consider that because I think that. So you were mostly interested in Liouville integrability, but I personally believe that this degenerate integrability or non-commutative integrability is more, in some sense, certainly different notion, and in a way it's a stronger notion because you have more integrals that you restrict the flows more directly.
And the other question, and something which we thought a lot about, and those days we were using these big, you remember these computer papers with confetti on the end, we were filling one up there. But the following question, which is an open conjecture. So the symplectic structure for real symmetric matrices is a Poisson structure associated with the lower triangle group.
Yes.
And of course, it's a degenerate structure. Conjecture was this: is the Toda lattice on every symplectic leaf completely visible?
Yeah, I think that's true too.
We also thought it was true.
But I think this is the kind of thing which I think recherches. I mean, there are some. Yeah, I can explain to you how I more or less can prove this kind of statement.
Well, that's for the general integration.
Yeah, but also there's such kind of statement that in the real analytic in the C infinity category, every degenerate integrable system is Liouville integrable.
What's that?
And every degenerate integrable system, in the sense of Nekorov-Shevin, it's also Liouville integrable in the C infinity category. It is proved. And in the real analytic category, it's a conjecture. It's not proof. So it depends also what kind of functions you allow.
Because we were doing it in a very hands-on fashion, just seeing how to take the problem in the most, in the largest case, and we generate, but we saw no pattern.
I did not really go into
was make sure we did it for staircase pattern, otherwise generic, but we never wrote it up. But it's true.
More basic is the quick question. The algebra theory, can you describe all the symplectic leaves?
Yes. So yes, indeed, here for the second structure, yes, this is one of the problems which I have to really describe the symplectic leaves.
But if I make a comment, so those coadjoint orbits of the Borel, and this was known for a long time to be wild problem. So, like in precise terms.
Yeah.
So which means that you probably cannot describe them in any satisfying manner.
Yet.
Okay.
But
but it's still wild. So
but I mean,
that's a statement. Yeah.
But of course, there is also such a thing as this so-called orbit reduction procedure that you fix the moment map to some coadjoint orbit, and then the quotient space of that is supposed to be, it's not supposed to, it is a Poisson submanifold in the space of orbits, but in the modern theory, it is not necessarily manifold, but then it is known to decompose the disjoint union of symplectic manifold. And there's an analog of this for the Poisson lever. And since my second structure really comes from Poisson theory with a moment map in the sense of Lu there, so I think there is a control of good Poisson subspaces in the second structure as well. Not a perfect control, but there is some reasonable control of that.
Maybe I'll venture a comment I shouldn't, but I will. Just about Percy's question, so the symplectic orbits, if you're dealing with this kind of dual Poisson group structure, are they not just the coadjoint orbits?
No, they are not. The dressing orbits.
No, I mean when I say the dual, I mean the dressing as the coadjoint.
Yes, that is the analog of the usual coadjoint orbit, the dressing orbit.
So the symplectics are the coadjoint orbits on the dressing.
In the dual group, and if you have the moment map, then you fix the moment map to such a dressing orbit, and you take the inverse image of that and quotient, and then you obtain a Poisson subspace in the quotient space, which may be this Poisson subspace. It could be a symplectic manifold also, or it's a stratified.
It's not classified. It is not classified. It's not known, but only symplectic.
Well, I did not really study it. Let me put it this way. It's not known in detail. It was not described in detail.
Thank you again.
Okay, thank you very much.
There's a coffee break now. Probably 10 minutes, half an hour.
So, you know the programs?
I copied it. It's so there. Just a second. So the next two terms are online.
You have a half an hour break.
Yes.